All right, welcome back, everybody. Here we are remotely, giving a asynchronous lecture here, I guess, due to some power outages due to the Hurricane Hillary. Looks like it was pretty dry today, so we probably could have done an in-person class, but better safe than sorry, and I apologize for any delay here. Have had some serious technological delays due to the power outages and kind of figuring out how to use the tablet again. But here we are. Should be kind of a shorter video because it's going to be only content and then the time that we spend in class kind of answering questions and kind of leading to the material rather than just giving it out. So it's going to be pretty content heavy, but it should be a little bit shorter. So I guess some announcements before we get started. So I posted on EdSTEM. The P6 deadline is now Wednesday, so it's due Wednesday at 12 p.m., so no late penalty for that. Just to accommodate for those that couldn't submit last night and had some outages. And because of that, P7 will be released Wednesday. So you can also look at the EdSTEM announcement for some more information there. I'm finishing up the midterm regrades currently. Midterm regrade requests, so there's some open regrade requests there I'm still working through. But yeah, hope to have that done by tonight. And then I guess we're going to continue sorting after this. So sorting lectures, it's going to be the last remaining topic from now until the end of the quarter. That kind of flew by pretty quickly. And so this will be the last topic on the final. So once we get to sorting, we'll kind of do an overview of what topics will be on the final, kind of like I did with the midterm, maybe discussion. We can do some practice or things like that. But yeah, let's go ahead and get started with today's topic, which is topological sorting. So let's see, up until now, so last time, we've kind of been doing these like DFS, BFS ideas. These are all fair game for the final. We've done Dijkstra's shortest path. So you should be very familiar with this algorithm, the runtime, why it works. It doesn't work for negative cycles, and the use of the priority queue in it. But today, we're going to be talking about a different kind of problem. So I guess there's this, maybe we can start with this observation about these real world problems, observation. So when we use, this is like the last graph lecture. So some real world problems can be modeled by what's called dependency graphs. By dependencies. Okay, we can look at an example of this. But yeah, in I guess more abstractly, kind of a dependency is like when something depends on another. So for example, I guess the running example for this lecture is going to be course prereqs, like prerequisites. So in order to take 31, ICS 31, here at UCI you have to take ICS 31 first. So this can be modeled using a graph, where a dependency is pointed to by the thing it's dependent on. So for example, 31 could point to 32, which could point to 33 if we're talking about classes. Another thing that's commonly used here is like jobs that you're going to execute. So like tasks or job, like if job 1 needs to be executed before job 2. For example, when you're like washing dishes, you first have to wash them and then you can dry them, something like this. So like scheduling, I guess, is another way of looking at this, scheduling or job dependencies. We don't really have a nice way of solving this problem, I guess, where maybe we can properly define it here. So if you have like a dependency graph, for example, where UV indicates V is dependent on U. The topological ordering problem, so what we're going to be doing today, sometimes called sort, topological sort, is like a list of all the vertices. So first of all, it is a list of all vertices, and for each like edge U to V, U appears sometime before v in the list. Okay, so this is kind of like the definition of a topological ordering for a dependency graph. The nice thing is I can kind of zoom to the next slide because you can pause and read this if you want to look at the abstract definition a little bit. I'm going to jump into an example that we're going to be using for the kind of the rest of the lecture. So for example, and to the best of my knowledge, this is correct because I looked at it on the website, but I'm going to use class prerequisites because that's kind of very, very pertinent right now, I guess, to your life. Prerequisites. So we have 31 must be taken before 32. Must be taken before 45 C, which must be taken before 46. That's kind of where we're at here. And 46 must be taken before 53. And also to take 53, you need 51 and 6b. And 51 is dependent on 33. 6b is dependent on 60. Surprisingly, I thought 6d was a prereq of 46, but I don't know. The website I looked at, I couldn't identify that, but maybe it is kind of implicitly. So this is not supposed to be a formal listing of the prereqs, but just for the example of the course. So what would a traversal or a topological order, so a topological order would look like 31, 32, 33, 45C, then 46. But notice we cannot use 53 because 51 has not been explored. So you need to do 6b, then 51, then 53, and then 6d. So let's look at our definition again. For each uv, u appears sometime before v in the list. So let's make sure that's true. So 31 must appear before 32 and 33, like so. 33 appears before 45c. So notice we cannot put 53 in. We need 51. So I think, this checks out. And this would be a valid topological ordering. Within the context of the problem, this would be a valid sequence of courses you could take while meeting the prerequisites, right? So this could be a course schedule. And maybe your course schedule looks a little bit more compact than this. But what's interesting is here's kind of like a critical path here. So this would be like the minimum number of quarters. Right, because these are all separate dependencies that you could fulfill to take the courses. These other ones can be kind of done in parallel at some point. This is sometimes called a critical path. And you'll talk more about this in your systems classes, but just kind of FYI, that's gonna come up. We're not gonna talk about critical paths here. We're gonna talk about how to generate the topological ordering itself. Okay, so a couple things about topological orderings before we go into the algorithm. So do all graphs have topological orderings? This is an interesting question to me. Do all graphs have a topological ordering? Maybe you want to pause and think about this before you go on. The answer is no, and that's because of cycles. Right, so if there is a cycle, no topological order, and that should make sense because if I have like this idea of a cycle, then which vertex should come first, right? We said each u must come before v in the ordering, but it's not clear which one should come first here, right? So DAGs, and remember trees are a subset of DAGs, and trees always have top ordering. And an important note is that the topological ordering is not unique, right? So you could imagine, in this case, 31 and 6b could appear in any order. I could have explored, 6b before 31 in this case, now it would still be a valid topological ordering, right? The whole idea is just that the dependencies are met before you get to each vertex, right? So if you get to a vertex and the dependencies are met, that's good, right? Okay, so solving top ordering. So let's solve this problem of topological ordering. The first idea that jumps out to me is this breadth first search, right? It feels like a very breadth first problem, right? Because you kind of want to go in order. But the problem with BFS is you need a start node. So remember, if you have some graph kind of like this, and the BFS explores layer by layer, remember? So the BFS would kind of look at this layer after the start node and then this layer, but you always need a start node to decide where the layers are going to radiate from. And the problem with topological sort is topological ordering is you maybe don't only have one start. So here, and it's not even guaranteed that your graph is connected, these dependency graphs, right? So 31 and 6b do not have any incident edges. So you would need some way for your BFS to explore both of those. And it's kind of unclear how that gets accomplished, right? So let's go on to idea number 2. So the other kind of search, unweighted search we had was DFS. So let's look at DFS. The pretty obvious problem is that this is a depth first, which means if you have this kind of abstract idea again, we're going to kind of hit a node, but we're going to keep going regardless of if there are other incident edges, right? So maybe this wasn't the best example, but if you had something like this, right, where this guy down here is incident on this vertex, it's not, the DFS is not really going to be aware of that, right? So there's no way for the depth first search to kind of know that this incident edge is here. But there is actually a trick we can do. So there's like a little insight here, very nice insight, is that the depth first search kind of does the opposite of what we want, right? So if we delay visiting, so what that means is if we were to look at each node or like reach each node, so we can start here, reach this node, and then reach this node. If we wait until we have a node where we've reached all the children, if we visit at this point, then we kind of have the opposite of what we want, okay? The opposite or reverse of what we want. So this is kind of abstract, I realize. So if we kind of label these nodes 1, 2, and 3, if we were to not delay the visiting, if we just immediately visit and then kind of recursively visit the children, we would see 1 first, and then 2, then 3, but we'd have the same problem as breadth first search, right? Where we wouldn't be incident edge aware. But if I were to do the opposite, where I look at 1, look at 2, look at 3, but only after, on the way back up, I visit 3, or like I report 3, so that 3 is the first thing, right? So 3 is the first thing I look at, then 2, and then 1. Then I essentially have the opposite of what I was going for, right? Along this path at least, and we'll kind of see how this resolves for the other edges. But we're going to use this kind of insight, and this is actually a repeat of a topic, and this was the post order, right? So if we can figure out how to get this post order idea, right? Remember from trees, right? A post ordering does all the children first, right? So if we were to kind of hit all these children first when we report them, right? And then the parent, we would have the opposite of what we want, and then we could flip it around at the end. Okay, so that's the insight we're going for. So the insight is that we're going to delay the visiting until after we kind of like search through the children. So very similar to post order. So we're essentially going to do post order for graphs instead of trees. And then we're going to reverse it at the end because that'll be the opposite, right, of what we want. So what does this look like? Let's see an example here. Okay. So let me just quickly redraw, maybe zoom out a little bit so I have more space. A redraw this graph, 31, 32, 33, 45C, 46. And then let's see, this was 53, which was dependent on 51. And yeah, feel free to skip this in the video if you just want to see the result. And then 33 was dependent on 51. Okay, so how the heck does this work? So let's take a look at our algorithm. So we're going to start with DFS, and then we're going to augment it slightly so that we visit like at the end, right? Okay, so we're going to have this visited equals here. Then we're going to have the like traversal. So this thing we're building up, which is going to be a list, right? Not a set, because we need it in order. And then we're going to have DFS with some graph G and a vertex V that we're going to start at. Okay, and the idea is you mark V visited, which essentially adds it to the set. Maybe I can just say visited V equals true. So mark it as visited. Then remember we did this in class for W and G neighbors of V if W not visited. So this prevents the cycles. Remember we kind of did this. Then we want to DFS GW. Okay, so now is where this insight of on the way back up, we want to add the thing to the traversal. So here is where we say traversal dot append V, right? Maybe you want to pause here and try to figure out why this is true for yourself before I explain it. But this is very similar to the post order. So if you remember for a tree, this is the recursion part for the tree. And then here's like the visit. It's the verbiage is a little different because in graphs, when we're visiting, we're just using this to mark whether we've seen something so that we don't loop. This is all for loops, right? But if you remember from post ordering, you had this pattern where you did the left and right recursion. Then on the way back up, you add stuff. And so if you think about how this resolves on the stack, you'll do like DFS for 31. We'll start at 31, right? So maybe we track here. 31 as a, so on the recursive stack, we're going to DFS for 32. We're going to DFS for 33. And then 33 has two children, but we can pick 45C. It's not going to matter which one. And then we'll DFS for 46. And then 46 has no children, right? So on the call stack, this is the first one's going to resolve. So it's the first one that's going to hit this append. So our traversal at the bottom is going to look like 46, right? It's the first thing that gets added because we're only doing it after the children have been visited, and 46 has no children, right? So this loop for the DFS 46 call will effectively get skipped, right? Because there's no neighbors, it's empty. Oh, sorry, no, there's 53. So there's 53 here. So I'm gonna leave that in just so you can see that I make mistakes too. It's okay. So 53 is the first thing, right? Because 53 has no outgoing neighbors. Okay, so then the stack is going to unwind, and we'll get 46 added, right? So very similar to the post ordering for the tree, and then 45C. So we can maybe track the stack here, right? And then we'll go back up to 33. Okay. So at this point, 33 is actually not going to get added because we had another call, right? So we're in the for loop for the 33 call. After the 45C, we'll explore 51. So then we'll add 51 here. And notably inside 51, we want to visit 53, but that has already been marked as visited, right? So 53 is already visited, so we'll come back out. All right, so this will be 33 here. And then we just follow back here at 31. Okay, so this is the traversal after we call this DFS with 31 as our start vertex. So what's interesting is this is not sufficient, right? It's the same problem as BFS, where we are not going to see 6B. Okay, so we have to slightly augment this idea to support multiple start vertices, right? And so how we're going to do that, I'm just going to use this space here, is we're going to have an outer loop that's going to do for v in g dot vertices. Sorry, let me make more space here. So for we need to call DFS GV. So you actually have to start the DFS from every vertex, because potentially every vertex could have no incident edges, right? You could have a fully unconnected graph like this, in which case it doesn't matter. The every ordering is a topological ordering, right? So it actually doesn't matter what order you explore in this. So that's kind of interesting, right? It's a little bit interesting, is that for a graph that doesn't have any edges, any ordering of the vertices is a valid topological ordering, because there are no dependencies, right? You can think about it that way. So you actually need to do this for each vertex. And so this would kind of go here, right? Like this would be some startup. This would be the main, right? Where you kind of run the thing on each vertex, where these are kind of global, or maybe context that's passed in. There's a lot of ways to do it. Maybe members of a class, somehow these get passed along as references or something like that. You've got a pointer to them. But we're going to keep adding to the traversal, right? So now we're going to restart the DFS at 6b. And so at 6b, like we're doing that post-ordering thing again. We've already seen 51, right? So it's in visited. The only thing we haven't seen is 6d. And then we'll see 6b at the end. And that will be exactly the opposite of what we want, right? And so this is a little interesting to me that this kind of works out perfectly to be the opposite, even though we didn't even think about the number of incident edges, right? We didn't like keep track. Have all the incident edges been explored? Because it doesn't matter. It's kind of guaranteed to happen by virtue of the post-order exploration, right? Because each child is emitted before the parent, you never have the case where the invariant is broken. Okay, let's kind of look at this invariant again. For each UV, U appears sometime before V. Okay, so all we're saying is if we're going to emit U, we better have emitted V first. And that's exactly what the post-ordering is doing on the way back, right? So using this thing at the end here, we're emitting the V. We have to be emitting the V, like at the very bottom, right? So 53 is the first thing that gets emitted, and it has to be before 46 and 51. Must be the case because of the post-order traversal, right? So as long as we're maintaining that invariant, and then we just flip it kind of around, we have exactly what we want. So I think that's really cool. So then at the end, you simply reverse traversal, and you have a valid topological sort. Okay, so I think that's really cool. I love topological sort because I think it's awesome how that works out. So if we analyze, that's not how you spell that. Analysis of the runtime. It should be clear. It's actually the same thing as DFS. Remember, we looked at this for DFS. Plus a theta V for reversal. And that's obviously dominated by the DFS. Right? So same runtime as DFS. We basically already learned how to do this. You just do this little trick of post-order emission instead of the pre-order emission, which I think we looked at previously. But you still need the visited to mark and make sure you don't run into cycles, just in case you didn't check for cycles beforehand. So I guess, in summary, topological order equals post-order in reverse. And because of that, it has the same runtime as DFS. No cycles allowed, because that just doesn't make sense. And it would break the algorithm anyways, so no cycles allowed. DAGs have top order and not unique, right? So no topological ordering is unique unless your graph is one path, right? So if you have this, then it is unique. You have like a strict ordering here, then it is unique. So I hope you learned something about topological orderings here. I hope that was digestible in this digital format, and you can kind of look through it at your own pace. And I'll see you all on Wednesday. Thanks for watching.